The world is going through an unprecedented transformation of its energy sector. We currently rely on an outdated, obsolete, and dirty electricity grid that was designed decades ago when the dangers of climate change were not understood. With increasing demand for renewables, the energy sector is in the middle of a seismic shift. Clean energy goals and the implementation of wind and solar energy are now at centre stage. However, significant challenges remain due to the intermittent nature of renewable energy. This chart explains why. It's showing demand for electricity at any given time during the day. The power demand is at its lowest during the night, then ramps up in the morning. Energy demand peaks in the evening when everyone returns home from work. This variation leads to mismatches in demand and the supply of renewable energy throughout the day. Battery energy storage systems provide the solution to this problem. During times of low demand, stationary storage batteries are charged to avoid curtailment. During peak times, the stored energy is sent back to the grid to make up for the shortfall. Lithium-ion batteries are currently the only suitable technology for this due to the high energy densities afforded. However, there are serious sustainability issues surrounding the chemistry. Lithium metal reserves are expected to encounter shortages in less than 65 years at the expected growth rate. There are also serious detrimental environmental and societal impacts related to the technology. An example of the unsustainability is the 500,000 litres of water required to produce just 1 tonne of lithium carbonate. So, to facilitate a truly sustainable future for the electricity grid, it's imperative that a green battery technology be developed beyond lithium-ion. Sustainable domestic batteries will allow for renewable energy to be optimized and used more efficiently. This will usher in the electricity grid of the future, where grid services such as peak shaving, peer-to-peer trading of energy, and arbitrage are readily available to the consumer. However, for this to become a reality, a holistic solution is required that encompasses not only a green battery chemistry, but also the hardware, software, and controller required to interface seamlessly with the grid and domestic renewable energy sources owned by the consumer. Introducing Trident, a grid-ready, sustainable sodium-ion smart battery for stationary storage applications. Unlike lithium-ion batteries, the electrode materials in the Trident battery are composed from highly abundant elements, are low-cost and non-toxic, and can be delivered using scalable manufacturing processes. The active materials are optimized for sustainability, consisting of a hard carbon anode recycled from bio-waste and a sodium iron sulfate cathode derived from iron sulfate, a low-cost additive used in the food industry. The ecological design of the chemistry will lead to a 50% reduction in both materials cost and global warming potential compared to lithium-ion battery manufacturing. Innovative approaches to tailoring these materials at the molecular level will allow Trident to achieve performance dramatically beyond state-of-the-art for sodium-ion batteries, with a specific ambition of achieving equivalent energy densities to present-day lithium-ion batteries. At a hardware level, a complete wireless battery monitoring system will be designed encompassing sensors incorporated at cell level, along with inter-pack networking, which will allow for an easy and efficient system-level integration. To couple the Trident smart battery system to the home and grid, a low-cost, high-efficiency grid-tie storage inverter system with inverter-stage power electronics and power switches will be also designed and proven. This system will be modular and implementable at residential prosumer level to enable the creation of a virtual microgrid with aggregated distributed storage. To fully integrate the system for domestic energy storage applications, a grid interface system for the Trident battery will be developed. Grid interfacing software will be demonstrated in the form of a flexible energy asset controller to translate commands from the grid and, using inputs from local power meters, adjust them as appropriate before relaying them to the inverters of the Trident smart battery. The scalable controller will allow the Trident smart battery system to connect to the electricity grid for a range of grid service applications. Today's grid-centric supply of energy is outdated and no longer fit for purpose, given the rapid rise of renewables. This centralized energy supply involves large-scale generation of electricity at a central power plant. The generated electricity is then transported over a distance through the electric power grid to the consumer, who sits outside the grid with no influence on its operation. Given the scale of the energy crisis, a revolution, not an evolution, in the electricity supply is required. Like all true revolutions, Trident seeks to put the power in the hands of the people, creating a prosumer-centric energy sector. The Trident smart battery system empowers the owner to sell or purchase energy to and from the utilities, creating a valuable energy flexibility that will reduce and optimize their bills. The Trident smart battery system can be used to store solar energy during the day when supply is high but demand is low. Similarly, during off-peak tariff periods, the battery can be charged at a cheaper rate. During peak periods, the stored energy can be used to avoid higher tariffs. The hardware and software will allow the Trident smart battery system to connect to the electricity grid to reduce pressure during peak demand by providing a range of grid service applications. This innovative plug-and-play solution provides flexibility to the user, opening up new markets that are currently unavailable to the prosumer. These include peak shaving, time of use cost management, flexible service applications, peer-to-peer trading of energy, operator grid management, and arbitrage. The Trident smart battery is a truly disruptive solution that will introduce flexibility to the energy markets, a key requirement for Ireland if the country is to meet its renewable energy targets. The system is disruptive at every level, with battery materials cost at 50% of conventional lithium-ion, sustainable electrode materials composed of abundant elements such as carbon, iron and sulfur, the anode material in particular being derived from lignin, a waste byproduct of the paper manufacturing industry. The battery is inherently safe as the gel polymer electrolyte eliminates risk of leakage and associated fire hazard. The battery chemistry will afford fast charge and discharge times of 15 minutes, suitable for stationary storage applications. The wireless battery monitoring system reduces cost of installation by up to 90%. Also, it reduces the total cost of ownership of the BMS and thermal management, including electronics, installation and maintenance, by over 50%. The grid tie inverter with low-cost silicon switches have an efficiency of greater than 99%, which is beyond state-of-the-art, and it's capable of delivering aggregated load demand in a virtual microgrid. The Trident smart battery system will also provide a flexible energy asset controller for grid management applications, and all of this in a single product designed exclusively to meet the challenges of the modern world. The Trident consortium provides experience across the battery value chain and is well placed to deliver on the ambitious goals of the project. The consortium consists of 5 SMEs, 1 multinational, 1 university, and 1 research institute. The University of Limerick and the SME Glantro bring materials expertise and will deliver the battery chemistry. The semiconductor multinational Analog Devices will develop the wireless BMS system in conjunction with the SME M Semicon. Voltage and temperature sensors will be incorporated into the BMS, and Analog Devices and M Semicon will work with UL to correlate the physical measurements with the state parameters of the battery. The SME's M Semicon, iCurgy, TESA Labs and mPower in conjunction with Tyndall will develop the power electronics and grid interfacing software. All partners will be involved in the prototype demonstration at project end. The Trident project is also connected to Midas Ireland, who played a key role in bringing the consortium together. Midas is an industry-led cluster consisting of industry, educational, research and government agencies working together to assist in the development of the electronics-based systems sector in Ireland. Midas recognised Trident's potential to have a profound impact on the green economy in Ireland and have fully endorsed the project. The economic opportunity for Trident is clear, with the stationary battery storage market expected to grow rapidly to $120 billion in the coming decade. There is huge opportunity in the distributed system flexibility market also, with an over $10 billion in savings estimated through residential demand flexibility, voltage support and peak management services in the US and UK. In Ireland, the effectiveness of implementing flexibility services has already been demonstrated by ESB Networks, with recent savings of $40 million on just 18 funded projects in the recent PR5 price review. As a result of these growing markets, the SMEs in Trident predict substantial growth in both revenue and jobs as a result of participation in the project. The SMEs' revenue is predicted to grow by almost $7 million by 2029, with 62 jobs created in the process directly as a result of Trident. To conclude, the consortium firmly believe that Trident will be a truly disruptive technology in the energy sector, providing a complete plug-and-play solution for grid-integrated battery energy storage systems. Sustainability and cost-effectiveness drive component design at all levels, leading to a best-in-class sodium-ion smart battery. We thank you sincerely for your attention and look forward to discussing our project with you in more detail now.